Today I'll continue the discussion on strain layers and then discuss what are the advantages of strain layers in quantum well lasers. That will bring me to the topic of quantum confinement in 2-dimension, 1-dimension and 0-dimension, and I'll discuss how these quantum well lasers operate and what are their advantages. At the outset, I want to emphasize that quantum well lasers are already incorporated into fiber optic systems. They are not merely lab curiosities. They are already in fiber optic systems in India, and Optel and HCL are using them in their systems. These lasers obviously work at 1.3 and 1.55 microns, and their advantages are very low line width, very high temperature stability, low threshold current, and very low degradation. So the physics of these lasers were worked upon, say, 15 years ago in the early 80s, but already there are various types of quantum well lasers that are in different systems. Let me start with a discussion of strain layers. I've already talked about what is the critical thickness of strain layers, how it can be calculated, the critical thickness, and then I've discussed the advantages of strain layers in lasers. I've jumped from the basic physics to applications. I've talked about what is the threshold current density, what is the gain of strain layers as compared with unstrained lattice match layers. I've talked about one system, germanium silicon, that is a very well known elemental strain layer system, but since these are indirect gap semiconductors, the more relevant system for optoelectronics is gas indium arsenide. Now you know that the lattice parameters of these are quite different. Okay, indium arsenide being material with indium which is larger than gallium, the lattice parameter of that is larger than that of gallium, which is 5.6535. Okay, so there's obviously, if you are trying to grow indium arsenide or even in gas, okay, if you are trying to grow in gas indium X gallium 1 minus X on arsenide, okay, it is not like algas, because as soon as you put in a little bit of indium, the lattice parameter will increase. Okay, so this is a prototype, a very intensely studied strain layer system, which is used because, what is the reason? That if it is possible to grow strain layers, then one can grow things like indium X gallium 1 minus X on gallium arsenide. Okay, and what will be the strain in this layer? If you grow indium gallium arsenide on gallium arsenide, how will this is the strain layer? What will be the strain? Will it be compressive or tensile? Yeah, this will obviously be, this will be compressive stress. Okay, but suppose you grow the other material. Suppose you grow, the same indium gallium arsenide on indium phosphide. Okay, we know that if it is 0.53, 0.47, this is lattice match system, right? Now, so in this, if you have, we are saying X is 0.53, suppose X is less than 0.53, okay, then on indium phosphide, what will be the strain in the layer? X less than 0.53. This is, it'll be tensile, right? Yeah. If this is lattice matched, indium is a larger atom than gallium, so this lattice parameter will be slightly smaller than that of indium phosphide, so it'll be tensile. Okay. And on the other hand, if X is greater than 0.53, okay, so it'll be compressively stressed. Okay. So these are the systems that have been intensively studied, both theoretically and experimentally. And in order to go from here to here, obviously, in this case, X will be typically something like 0.2. Okay. Okay, because if you want to stay within a critical, small critical layer thickness, then X will be 0.2. So you're looking at strain layers with different values of X. What people are trying to do are grow layers on gallium arsenide rather than indium phosphide, because the bulk quality of gallium arsenide is much better than indium phosphide. The cost of gallium arsenide substrates is much less, factor of 3. So people would prefer to grow on gallium arsenide rather than indium phosphide. Okay, this establishes the motivation for looking at these strain layers. Let me just go into a little more detail about this indium arsenide gallium arsenide system. This has been studied in great detail, and I was writing down the values of lattice parameter A0 in angstroms. C11 and C12 are the elastic stiff,Cij's are the elastic stiffness constants. And I'll show that obviously when you're talking about strain, okay, the amount of strain will be dependent upon the elastic properties, and these are measured in 10 to the power 12 dynes per centimeter squared. Okay, these values are known, C12, this is, and the interesting thing is that these values are quite distinct. Okay. Xi is hydrostatic deformation potential. Okay, this is hydrostatic deformation potential, which is how the material responds to uniform hydrostatic pressure. B is the shear deformation potential. And these values are well known for these materials. Here, this is -6, it's -8.2, -1.8, -2. Okay. Effective masses, relative effective masses, indium arsenide, very high mobility, so low effective mass, 0.023, gallium arsenide, 0.069. These are connected with the mobilities. Hole effective mass, relative 0.41, 0.47, almost the same. And this is the light hole effective mass, I think, 0.027 and 0.074. Okay. So the properties of indium arsenide and gallium arsenide are quite well known. Why are these parameters important? Because it turns out that due to strain, the change, last time I discussed how the band structure changes with strain, and the change in the energy of the heavy hole band, delta EHH, is given by a relation of this type, -2 xi epsilon C11 minus C12 over C11 plus B epsilon C11 plus C12 over C11. Okay, where epsilon is the strain, is delta A by A0. All these parameters are known for this gallium arsenide, indium arsenide system. Similarly, delta E LH, the change in the light hole band energy with strain, is given by this expression C11 minus C12 over C11 minus B. Okay, and this immediately twice C12 over C11, and this immediately, this is shifts with respect to conduction band edge. So this illustrates the fact that these values, shifts, can be calculated. And for example, if you think about the overall band gap, I talked about the silicon germanium system last time, going for X going from 0 to 0.5 in the system, indium X, gallium 1 minus X. Gallium arsenide band gap about 1.40 electron volts. Okay, and if it is an unstrained system, the band gap varies something like this. And if it is a strained system, this is obviously about 0.7. So the change of band gap of this alloy when it is strained and unstrained, it can be calculated. Now when we are making quantum wells or even heterojunctions, what is important is, for heterojunctions, we are interested in these conduction and valence band offsets. Okay. Suppose this is gallium arsenide, okay, and this is in gas. Obviously, this will be strain layer, and these band offsets will be determined by the strain. For example, it's known for indium gallium arsenide that the band gap as a function of obviously X is 1.424 minus 0.162 X minus 0.56 X squared. Okay. Now, if we look at these band offsets, delta EC and delta EV, it's found that strain, okay, this is 0.03, this is delta A0 by A0, okay, as a function of X, it goes something like this, okay, for X going to 0.5, goes like that. Okay, now suppose you want to plot the valence band offsets that I showed, again as a function of X. Okay, sorry, this is 0.2. In gas strain layer system, delta E LH goes something like this. It's given by the relation that I presented earlier, and delta E HH goes okay. So this is an example of what is known as band structure engineering. By changing X, you are changing the strain, and thereby you're changing the light hole band and heavy hole band offsets. Okay. To repeat overall the effective strain, this is what I discussed last time. Suppose you have an unstrained layer, okay, where here's a conduction band, okay, and suppose this is the heavy hole band, and this is the light hole band, okay, and this is the split off band. One easy way of remembering this is unstrained. And we'll talk about compressive and this is compressive and tensile. Okay. Now we know under compressive strain the band gap increases. Okay. So as a result, here this band we will show that it goes something like this. Okay. So under compressive strain, this band gap will go, the conduction band edge will move up, okay, and the valence band edge will move down. This is moved down. It's drawn slightly exaggerated, and there will be splitting of the heavy hole and light hole bands. This is heavy hole and this is light hole. This is the split off band. Okay. In this case, the heavy hole band will be on top, and the light hole band will be somewhere here. The split off band will be lower down. Okay. And with this is with tensile strain. This is the unstrained region, and it will go say something like that. This is a little exaggerated. However, if I draw the strained region somewhere here, tensile, okay, what happens? The band gap decreases, and here it is the light hole band which is on top. Okay, the heavy hole band is, and the split off band also follows a particular variation. Okay. Okay. So here, excellent strain XX. This is only in the. This is XX less than 0 compression and XX. Okay, this epsilon is delta A. So delta A is compressive. So delta A is negative. Okay, delta A by A, so it's negative, and this here delta X, epsilon XX is greater than 0. Okay. So this, in a nutshell, is the effective strain on the band structure. Now, what effect does this have? Last time I already discussed finally what happens in lasers, but before going into that, let's look at the different physical effects. One is band gap changes. Okay. Oh, not even band gap. Okay. But it is light hole, heavy hole degeneracy lifted. Okay. Then the effective masses also change. Okay. Remember, effective mass is a fundamental property which determines things like mobility, etc. So the effective masses also change. And so since the effective masses changes, I'll show that what happens is that the in lasers, population inversion condition changes. Why? Because this is connected with the density of states. Density of the effective mass change determines the density of states. Okay, and the population inversion condition also is determined by density of states. So the density of states is a function of energy changes, and we have, I think, delta G delta N, the differential gain increases. Okay, I won't give you a table. Like there are values given in Pallab Bhattacharya's book as to how this effective mass changes. Well, I don't know if I'll. Okay, yeah, okay. I'll just give you just a. I won't give you the entire table, but I'll just give you a glimpse of this for indium gallium arsenide, say X. Okay. M star unstrained. Also, the effective mass becomes anisotropic. Okay, in the layer plane it is one thing, and perpendicular to the layer plane it is another thing. Okay, because the crystal structure is not cubic; it's tetragonal. So for X is equal to 0, no strain. Okay, so this is 0.066, 0.066, 0.066. Okay, suppose X is 0.4. Okay, strain layer, then this becomes 0.050. This is 0.057 and 0.0060. Okay, so there is more than 30% change. Okay, 30% change between due to X, and here there will be about 10% change due to strain. So this is quite significant, and it has to be taken into account. Quite apart from these, the effects of strain is that some of the non-radiative recombination mechanisms. Okay, let's not talk about that. We'll, like Auger, that is reduced. But one major effect is intervalence band absorption, which is called IVBA, is reduced. Okay. What is this phenomena? This is due to the fact that when if you have a conduction band and here are the two valence bands. This is the split off band. Okay. When light is emitted, okay, this can give rise to self-absorption. This light can, due to electron-hole pair recombination here, this light can be used to excite a hole from a split-off band here. Okay, so this means that effectively the radiation efficiency is lowered. Now, if suppose you go to higher band gaps, this is even more pronounced. What is the effect of strain? The effect of strain is that the band structure is changed, the valence band structure is changed such that the density of states here is reduced, and this split off band goes down, such that this intervalence band absorption is no longer possible. This is strained and this is unstrained. This is due to two phenomena. One is this peaking in the density of states here, so that you don't get a variety here. There is a possibility of, okay, this is E versus K. Okay, here there is a possibility that you get recombination there, okay. So there's a variety of different energies which are possible. Okay, so this variety of spread of energies will give rise to absorption there. Here, the probability is only limited to a particular energy. There's a limitation in the energy of recombination, and that energy is not sufficient to create this IVBA. Okay? So this is quite important for 1.3 and 1.55 micron lasers. Okay. If this occurs, IVBA occurs, then the threshold current increases, and it reduces the quantum efficiency above threshold due to this inter-subband absorption. Okay. The other important effect is that Auger recombination is reduced this is due to the fact that the separation between band edges and the split off band and remember this Auger recombination is quite important in low band gap materials. So we have the phenomena that this is a conduction band. Okay. This energy can be transferred to say another hole here, which is given additional energy to move off. Okay, and sometimes if you have an electron in the light hole band, this can get this energy from electron hole recombination. In the case of with strain, what happens is let's see. The heavy hole band and the light hole band are separated, and this energy is band gap increases, okay, over beyond this, and as a result, the coupling between the heavy holes and the light holes, this is reduced, so that this Auger type of process in which this is unstrained. This lifting of the degeneracy here reduces this probability of this Auger process. That is one, and the band gap increasing also results in a decrease in the Auger process. Okay, so these are two major effects, and I'll just mention there is also effect on the polarization. Last time I gave a plot something like this. In gas system for x is equal to 0.53, this is compressive and this is tensile. And we showed that the polarization showed a variation something like where the polarization was given by the component T component over TE plus TM. Why is this? Now from this you can gauge that T component it couples strongly with the heavy hole band, and the TM component it couples strongly to the light hole band. Why is that? If you look at the structure of the layer, suppose this is the Z growth direction. Okay. This is the X and this is the Y. What I'm saying amounts to that this Z growth direction couples strongly to the TM modes, and the Y direction in the plane, where this is the plane of the layer, couples strongly to the TE mode. And the effect of stress is compressive stress gives more TE-like, and tensile stress gives more TM-like behavior. That is obvious from here when we are saying that, okay, as compressive stress increases, we are getting more T-like behavior rather than TM. This is really explained by the nature of the wave functions. Okay, if you look at the I have not discussed polarization in great detail apart from when I was talking about propagation. Suppose we look at the transition matrix element, okay, for conduction band to heavy hole transitions. Okay, that matrix element for transition between conduction band and heavy hole has a geometry something like this. It is like a donut. Okay, it is like this. And this matrix element MT squared is equal to 0 for E parallel to K. Okay. So when E is parallel to K, I'm talking about, in the center of this, okay, this function is a minimum. And this is a maximum when E is perpendicular to K. Okay. So in this direction, it's a maximum. Okay. What about if you look at K for the conduction band, light hole band, matrix element. That is depicted by sort of barrel-like figures, okay, of this type. And the properties of this matrix element is just the opposite. MT squared is maximum when E parallel to K, okay, this way, okay. And this is equal to, it's a minimum, it's not 0, it's minimum when E perpendicular to K. So this has got to do with the conduction band. Remember, the conduction band wave function is S-like. Okay, the valence band p-state wave functions they're obviously p-like. You have px, py, pz components, and so if you using the wave functions you calculate the matrix element, then the transition strengths can be plotted as a function of, okay, for this is for K parallel, C to heavy hole band, okay, and this is for low values of K, this is TE-like, and this is TM-like. Okay. Whereas for conduction band to light hole band transitions, we have just the opposite. It is much stronger TM here. Okay. And this is TE. So this just illustrates that the effective strain is not only to change the JTH, delta G, delta N, but also to change the relative polarization strength TE over TE plus TM. And to end, I will just, I think I'll draw that diagram that I drew last time. That it's found strain has a drastic effect on in-gas system. X is equal to 0.53. Lattice matched. This is lattice matched. Okay, this is tensile. This is compressive. And it's found that there's a drastic reduction in JTH when you have compressive strain. So these lead to distinct advantages of using compressively strained layers in lasers. There is another very big advantage that I'll come to later on, that is regarding reliability. Okay. What are the degradation mechanisms? Some of it is due to dislocation movement from the substrates or in the epi layers. If the dislocation can be easily created or they can move, then degradation occurs. And it is found that compressive strain gives much lower degradation. On the other hand, if you have a tensile strain, okay, if a layer is under tensile strain, it seems that dislocations can move much easier and you have higher degradation. Okay, with time, that when you're working with a laser, you're using it as the high power levels for a period of time. So here again, compressive strain is preferable to tensile strain.